Hey everyone, I just wanted to run through the sample final so that we have an idea of how to do all these problems, and let's get into it. All right, so we have two functions, h and g. Let's see, the function g is the graph, and then h, this one, is an invertible function. Okay, fine. So g of 0, don't be tricked, it's not that, it's 3 apparently. So that's the filled in dot. Hopefully they'll ask for the limit as x goes to 0, maybe not. No, okay, so the limit as x goes to 0 of g is 0, but they don't ask for it. The actual value is where the black dot is. Okay, g of 2, that is undefined. That's a trick question. This here is an open dot. There is no black dot for g of 2, so it doesn't exist. H inverse of negative 2. So this means you want to go from the right column to the left. Okay, so H goes this way, H inverse goes this way. All right, so negative 2, we find it. We go over here, 0. Boom. All right. H plus g at negative 1. So h of negative 1 is negative 3. And g of negative 1 is positive 1. So we get negative 2. All right, h of g of 1. So first we find g of 1. G of 1 is 1. So this is the same thing as h of 1 because g of 1 is 1. So what is h of 1? Well, we hop over here. H of 1 is 3. Okay. All right, this last one is negative 1. You don't even have to look at the table. Anytime you have a function and its inverse, they undo each other. And so whatever you input is what it outputs. Okay, let's compute the average rate of change from negative 2 to 0 on h of x. So this is h at negative 2 minus h at 0 over, I guess I should actually go the other way. It doesn't matter as long as you're consistent, so don't worry about it. You can do that, or you can do this. Sorry, this is what I was just trying to say that you don't have to worry about. So this is why you don't have to worry about it. Both of them work. You just have to be consistent, meaning same x values, okay, lined up. Okay, so what do you get? Let's see. H of negative 2 is negative 5. H of 0 is negative 2. So I have negative 5 minus negative 2 over, and then minus 2 minus 0, that's minus 2. And so what's this? That's 5 plus 2 is negative 3 over negative 2. So we can just write it as 3 halves if we want. Okay, fine. All right, so function g this time, minus 1 to 1. So minus 1 to 1, this line segment here is what we're interested in. We want its slope, and it's 0. So 0. Okay, illustrate the meaning of this value. Okay, compute. You have 1 minus 1 over minus 1 minus 1. That was g of negative 1, and that was g of 1. The difference in y values over the difference in x values. The y values are the same, so you get 0. So we've computed. Illustrate the meaning of this value on the graph. So here is the average rate of change minus 1 to 1 of g of x, and it's illustrated because it's this horizontal line. Okay. Rank the following below. So we got the slope from 1 to negative 4. So let's clean this up for a moment. All right, from 1 to negative 4. So we go from that dot to this dot. Okay, that kind of looks like that. And so it's sort of like a, since we're going from 1 to 4, well, whatever. What's the slope of that line? It's sort of like a shallow negative. Okay, I don't actually care what the number is. 1 to 2.5 of g. Okay, so 1 to 2.5, that's like this. That's a pretty steep positive. Okay, so it's like a steep positive. And 3 to 1.5. Let's see, 3 to 1.5. Okay, that's pretty dang close to 0. So it looks like it's going to be the shallow negative, then the thing close to 0, and then the steep positive. These are all different slopes, and so I sort of know this is like a negative number that's kind of close to 0. This is a positive number that seemed even closer to 0, and this is a positive number that seemed far away. So anyway, All right, consider this updating function. Sketch a graph of the updating function, correctly labeling the axes. Okay, so correctly labeling the axes, our input is called c sub t, so that's the label of the input axis. Our output is called c sub t plus 1, so that's the label of the output axis. That's it. You're going to get at least a point or two from doing that. All right, so now let's graph this. We have a y-intercept of -3, so we go down here, and we have a positive slope. Don't overthink it. Just sort of draw a line, okay? That's all they're going to look for. They want to make sure you should label this. But because there's no grid, okay, they don't care about you putting a grid. They just want to see a positive slope. And in fact, so what's important is that this is steeper than 1. Okay, so the reason that's important is because this line has slope 1. Okay, this is the line y equals x. Technically, it's the line c sub t plus 1 equals c sub t, but whatever. It has slope 1. So if I have a y-intercept of -3 and I draw slope 1, I have two parallel lines. Okay, it's important that this slope is steeper than 1. It's important that we're steeper because that way we'll intersect. So we're going to do something steeper than 1 like that. So that's all they're going to really look for. Like, they're not going to actually compute and check to see that you have the right slope. They just want to see something steep enough to intersect and something that hits down here to negative. Maybe we should label where they intersect, but honestly, okay, yeah, so it's going to come up later. It's the equilibrium point, so we'll get to it. All right, if C0 is equal to 4, fill in the table. Well, okay, here's T, so that would be our subscript. So this is talking about C0, and they just said that was 4. Okay, so if T is 0, then we have C sub, and 0 plus 1 is 1. I'm looking here and plugging in 0. So C sub 1, oh, we have this updating function. It's 2C0 minus 3. So that's 2 times 4 is 8, minus 3 is 5. And then this number goes right here. We're doing Euler's method, but you don't know that. Okay, so now that's C sub 1. And to get C sub 2, I'm going to do 2 times 5 minus 3. That's 7. So 7 goes here. And to get C sub 3, we're going to do 2 times 7 minus 3. 14 minus 3 is 11. Okay, so now we got C sub 3 is 11. Sweet. Find the equilibrium point of the system algebraically. Okay, so equilibrium point means the input, let's call it C. Don't worry about the T. So if you input that number C, it'll be the same as the output. You get C back out. Okay, so solving it algebraically means we need to solve for C now. The textbook likes to use C star, so I'll use C star, but I personally hate having to write more than I need to, so I don't like the superscripts, but whatever. All right, let's subtract C from both sides. Minus C, and let's also add 3 while we're at it. Plus 3, plus 3. So now the 3's over here, and then 2C minus C, that's just C. Hey, we have now solved algebraically. Okay, you must show the equation you are using to find the equilibrium point. Okay, we did. As well as solve the equation. Okay, we did. So, all right, let's use cobwebbing to check it out. And so what we do is we pick a spot that is not, okay, so right here's the equilibrium point. This is 3. We move to the left a little bit and pick a starting point, okay? Now you go vertical to your updating function. So vertical to where you've drawn, and then horizontal to the line y equals x, and then repeat. Vertical, right? Vertical doesn't mean up, it just means up or down. So this time I had to go down, and then horizontal. Vertical, and you get it. So we're traveling away. So far we've got evidence for unstable. And since those are the only two options, we can go for it. But really we should check on the right as well. So we go vertical to updating function, horizontal to y equals x. Vertical to updating function, you can see. In either case, we're going away. It's unstable. All right. So it says use cobwebbing, so they're expecting that drawing. So it's important that we know the steps. Vertical to updating function, horizontal to y equals x. Classify the point, so we've done that. You must identify the point from the previous problem on your graph, clearly illustrate with cobwebbing. Right. So I would argue this pretty clearly identifies it, but if you're worried, you can say, hey, this is the point 3, 3. If your input is 3, your output will be 3. That's why we don't worry about the subscripts when we solve for it, because it doesn't matter what t is. No matter what time you hit 3, it's going to stay 3 forever after that. All right, So that's a review of midterm 1 material. Midterm 2. So use the graph function, answer the questions below. Right does not exist if the value doesn't exist. So let's take the limit as x goes to 0. So limits are predictions. So if I let x get closer and closer to 0, and I live on this graph, my prediction is that I'll touch -1. Same kind of thing here. If x gets closer and closer to 3, and I live on this graph, my prediction is that I touch -2. Predictions don't mean they actually come true. It's just what it looks like is going to happen. Okay, so now x is going to go to -1, but the way we're going to do it is from the right. That's what this little superscript means. So let's find -1. Here it is. And notice, right, if I come in from the left, it looks like I'm going to hit +1, but we're not coming in that way. We're coming in from the right, and it looks like I'm going to hit 0 for my y value. So this is a 0. All right, this fancy combination of symbols here with the limit of h going to 0, that is the fancy way to say the derivative at -4. And that's a fancy way to talk about the slope on k of x at x equals -4. Do not write this on the test. I'm writing this for the audience, which is you. So, hey, -4, if I'm right here, does it make sense to talk about its slope? No. There's more than one option. It doesn't exist. So that's a trick question. The derivative does not exist there, does not exist, and it's because we hit a corner. Okay. But you could think of it also as the slope is not defined, right? I can't pick one line and say that's the slope, whereas like, other spots, even if they're curvy, if you just sort of zoom in enough, it'll look like a flat line, and that is what I like to call the flat earth lemma. That's the whole point of calculus. Okay, whatever. Let's hop over here. The slope at -5. Hey, I can talk about that. That looks like I go over 1 and up 3. Okay, that's a slope of 3. Boom. The concavity at 4. Oof, if he wants equals, I bet it's a straight line. And what do you know it is? So straight lines have a concavity of 0. Said differently, straight lines, so these are things that look like y equals mx plus b. If you take one derivative, it'll pluck off the number that is the slope. And if you take another derivative, it'll be 0. So anytime you have two derivatives and there's a straight line happening, you're going to get 0. All right, so now we define a new function, and we're going to plug x squared into k. Fine, whatever. Let's take a derivative. So this is the derivative of the outside, so that's k prime. You leave the inside alone, times the derivative of the inside. That's a chain rule, super important. Brush up on that if you don't know it. It's the most important thing in calculus. All right, so now let's plug in 2 for x. So what we're looking for is k prime at 2 squared, which is 4, times 2 times 2, which is 4. Okay, so what is this? K prime at 4. Did we previously compute that? We didn't, but that's okay. We can look at it here and compute it. It looks like we go over 1 up 2. So k prime at 4 is 2 times 4 is 8. Sweet. All right. The second derivative at 0 is, so notice they're not looking for a number. They're looking for a description. Positive, negative, 0 doesn't exist. So let's hop over here. Let's look at x equals 0. And this is looking concave up when x is equal to 0. So concave up, that's a positive second derivative. All right, we're given the slope at 0. Write the linear approximation. So this, by the way, is like taking one step of Euler's method. So I just want to keep referencing the new material. So what do? You take the starting y value plus the slope at that spot times, and we want approximation L of x, so the change in x used to be 0 and now it's x. Okay, so let's plug in everything we know. What is k of 0? It's -1. Right, here it is. What's k prime at 0? It's -1/2. And then x minus 0 is just x. So there's the equation. Sketch and label this tangent line on the graph. Is L of x an underestimate or overestimate? Okay, sorry. So we hop over here, boom, boom, sketch and label. So we're right here, and we have a slope of -1/2. So I'm going to give myself another point to shoot for, where I go down 1 and over 2. And in fact, let's also go over 2 and up 1. So I'm going to shoot for this point as well. So here we go. Boom, 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 boom. So we're looking for something like that. We should have some tangency here. We should have a slope of -1/2. There it is. And the question was, essentially, is this line we just drew, is it below or above the black curve? And it's below it, so it'll be an underestimate. But we can also see that if we were to mark it, sort of like right here is L of 1/2, but above it, very mildly, right? I have to like zoom in a bunch, but this is K at 1/2, okay? So we had an underestimate here. All right, so now we have an updating function has equilibrium point blah and blah. Write the updating function rule as f of x. Okay, well, f of x is the output, and if you input p sub t, but you call it x, then what you have to do is multiply by 3, and you have to square it and take their difference. Okay, now let's compute the derivative. So f prime of x is 3 minus 2x. According to the stability theorem, what can we say about this? So we have to look at the slope at 0, the derivative at 0. We get 3. And an important little fun fact about 3 is it's bigger than 1. So this is unstable. So we should say, bigger than 1 is unstable. All right, and so you must show all your work. Our work was we plugged in 0 and realized it was bigger than 1. Okay, that's what they're looking for. How about 2? Let's plug 2 in. So we have 3 minus 4, because that was a 2 times 2. We get -1. -1, the fun fact about that is that it equals -1. So what we care about, sorry, this is f prime, we care about the absolute value of f prime of 2. That's equal to 1, and that's inconclusive. So, right, let's just review the stability theorem really quickly. If you take a derivative of your updating function and you plug in your equilibrium points, then you take the absolute value of that. If it's less than 1, it's stable. If it's bigger than 1, it's unstable. And if it equals 1, it's inconclusive. Okay? So, sweet. On to the next one. So here's a function. Explain why x equals 2 and x equals 4 are critical numbers. Okay, that means the derivative, when you plug in 2 or when you plug in 4, we had better get 0. Okay, so that's what we need to check. All right, so let's just check this. So we should take a derivative. L prime of x is equal to, and it looks like it's x squared minus 6x plus 8. And hey, by the way, what do you know? That factors as x minus 2, x minus 4. So, in fact, if you plug in 2 or if you plug in 4, you would get 0. So that's true. All right, use a first derivative sign chart to classify these things. So, here is the x-axis. And right here is 2, and right here is 4. So, what can we say about the sign of f? In fact, look, this is not what they want because I'm going to do more than a sign chart, but we have a parabola that opens up and it hits 0 at 2 and 4. Okay, so this is f prime. So now what they want is what I'm going to write in black. Okay, so this is what they want, and they want to know the sign of f prime. Well, if you look at that blue curve that I drew, it's positive when you're to the left of 2. It's negative when you're between 2 and 4, and it's positive again over here. But all you really have to do is just pick any x value here. Like let's say x was -100, and you plug it into your derivative function. So if I plug x equals -100 in here, well, this would be a negative number, and this would be a negative number. And a negative times a negative is positive, and so that's this positive here. But if you know you have a parabola that opens up, then you sort of know you have this shape, and so you know you're up here in the positives when you're in this region. So anyway, you can plug in numbers, or you can sort of know what a parabola looks like. But regardless, we now have the sign of f prime. That's telling you about the slope of f. So let's draw the slope of f up here. when the slope is positive, f be doing that. When the slope is negative, f be doing that. And then it's positive, f be doing that. So this 2 had better be a maximum, and this 4 had better be a minimum when we're talking about the function f. Sorry, my penmanship is getting worse. So did we just classify these? Yes, we did. I labeled 2 as a max, and I labeled 4 as a min. And did I use the first derivative sign chart? Yes, I did. That's this stuff in black where you mark off your critical points. You put down the sign of your derivative values, and you use these to draw the arrows talking about how f moves around. Okay. At what values do the absolute maxima and absolute minima of L of x occur on the interval blah? Okay, and notice, important about this interval is there's no 4 in here. So we don't care about x equals 4 anymore. We care about 0. We care about 2. That was one of our old critical points. And we care about 3. So in general, when we want an absolute min or max, you test your endpoints and you test critical points in the interval. So what do I mean by test them? I mean, just plug them in your function. Actually, I called it f down here. I should have been calling it L, whatever. So sorry about that. When I say plug in, we need to compute L of 0, L of 2, L of 3. I don't want to do that, so you should do that. Just plug in 0, and then plug in 2, and then plug in 3. Take the biggest, that's the maximum. Take the smallest, that's the minimum. Okay. I guess if you plug in 0, you get -4. And if I plug in 0, that's over here. So I'm going to be going up until I hit 2. I bet 2 is going to be the max. And then I start coming down. So, fine. So 2 is going to be the max. What happens if I plug in 3? 20, that's 9 minus 20. That's a pretty big negative. Oh, that's a pretty big positive. I think this one's going to be the min. So that's my guess. But, okay. Just plug them in, take the biggest, take the smallest. All right, new material. Finally, we made it. All right, for each limit below, write a new limit using leading behaviors. Okay, so what do we need to know about leading behaviors? Exponential stuff leads the pack. I was thinking of this symbol. This symbol, I mean, like, as you take the limit, as x goes to infinity, this stuff leads, okay? It dominates. But actually, I guess our brains tend to order from left to right. So let's go slow first. Logs are the slowest, okay? Then you got polynomial stuff. Then you got exponential stuff. And included in this land, you just order by the exponent. So like root x, which is x to the 1/2, that's going to be less than like x, which is going to be less than like x squared. So, right, all of this, there's like a whole family in here that I just didn't feel like writing. So, broadly speaking, this is sort of the pattern. My cat is on something right now. Okay. So, leading behavior, we look for what grows the fastest. We're going to go this way. Okay. So, the square root grows faster than natural log x. The exponential grows faster than a power of x. So, this becomes the limit of root x over e to the x. It says write a new limit you do not need to compute. So I won't. But by the way, this will be 0. Okay. Same idea. We ask what grows the fastest. And this is, so here this is as x goes to infinity. If x goes to negative infinity, some stuff gets flipped around a little bit. So now, I'm just going to say think about it rather than give you rules. Here's the thing. 0.5, that's really 1/2 to the x. If x is negative, then this is sort of like you'd flip it back over to a 2 and then take the absolute value of x. This thing is going to grow as x goes to negative infinity. And in fact, it's going to dominate x. So 0.5 to the x, that's what grows. Oh, fine, let me talk about this. Here, you need a bigger than 1. And now if we shoot off, whoop, x is going to go to negative infinity. Negative infinity, sorry. Now you want a less than 1 to the x, and that thing's going to blow up, okay? And you'd want like 1 over x to, no, that'd be for 0, sorry. Then you have x to the n. Logs don't make sense when you have x, so sort of you can just remember this, and that's probably all that we're asked for in this class. All right, that thing's going to decay. This thing's going to decay because the base is bigger than 1, and so when x is negative, it's actually like a 1 over e to the absolute value of x. So that's why that's gone. So it's going to be this one, x to the 100. And then what's going to happen is the bottom would blow up and win, but you don't need to know that. It doesn't ask for it. Okay, explain why L'Hopital's rule can be used. Oh, so we should be thinking 0 over 0 or infinity over infinity to compute the following limit. Then compute the limit. Okay, so why can it be used? Here's the rule. You plug in the x value, e to the 0 minus 1 sine 0. And if you get either this or that, so 0 over 0 or infinity over infinity, it can be used. So that's what we want to check. E to the 0 is 1. 1 minus 1 is 0. Sine of 0 is 0. So explain why L'Hopital's rule can be used. So because when you plug in 0, you get 0, 0. And the fancy word for this is so it cannot be determined. It is indeterminate. Don't worry about that. You don't need that. It's indeterminate form. It's the one that tells you can use L'Hopital's rule, but this is good enough for sort of this part. Now we need to compute it. Okay, so this is equal to. Let's use L'Hopital's rule. L'Hopital's rule says take the limit still. We're going to have to do that. But the function on top, take its derivative. The derivative of e to the x is e to the x. The derivative of negative 1 is 0, so it's gone. The derivative of sine is cosine x. And if you can plug in your x value and get a number that makes sense, that's the limit. And that's exactly what can happen here. So e to the 0 is 1, cosine is 1, your limit's 1. Okay. If you don't know that, and you have this, just start to plug in really tiny x values into this function and see what you get, and your calculator will be telling you it's like 0.99999. So that you should plug in like stuff like this, okay? Like get really close to 0. All right, consider this differential equation with the blah. Use Euler's method with the blah to approximate the blah. Okay, Euler's method. This is linear approximation. We just sort of do it over and over again. So let's make a little table. We've got x values, boom, boom. We've got y values. Actually, we should call them k because we care about the function k. We've got k prime, which we're going to compute via this, okay? And then we've got the new k. So this column is going to be k of x. So for example, when x is 0, k of 0 is negative 1. And, okay, what's the slope? This is also at x. So the slope at x is 5 minus 0 plus 0, because, again, x is 0. Okay, so that's just 5. All right, so now k at x plus delta x, okay, which is the new x value. So delta x is 1. That's this. So we have 0 plus 1 is 1. So here we're looking at k of 1 because I plugged in 0. That's the x value I'm at. I plugged in delta x. That's this thing. Okay, this is going to be equal to, and this is where we use linear approximation. So it's your old k of x plus your slope times delta x. Okay, so k of x, that's this number here. So it's negative 1 plus k prime of x, that's this number here. So it's 5 times, and delta x is 1. They're being very nice, 1. So negative 1 plus 5 is negative 4. Okay, so negative 4 is k of 1. That's what we just figured out. You're always going to take this number and plug it in here. Okay, so k prime at 1. So now I have to plug in x equals 1. 5 minus 4 plus 12. That's 5 plus 8 is 13. Really, I should have done 1 plus 12. All right, and now k of 2 is the old k value plus the slope times delta x. So 13 minus 4 is 9. That's the answer. K2 is approximately 9. All right, find the specific solution for k of x using the antiderivative. Okay, so k of x, well, it's kind of like the antiderivative of k prime of x. And I'll explain what I mean by kind of like. So let's find the antiderivative. That function was 5 minus 4x plus 12x squared. Okay, so let's find the antiderivative. 5 becomes 5x. Here I'd make the power a 2. Divide by 2, you get 2 instead of 4. Make the power a 3. Divide by 3, you get 4 instead of 12. And you have this pesky plus c. Okay, plus c. Boop. And in fact, you could actually just write is equal to here. But we need to pin down this c. That's why previously I had is kind of like. So how do you pin it down? Well, you plug in 0 for x. So now k of 0 is equal to, I'm going to plug in 0 for x. That's 0 minus 0 plus c. And that needs to equal -1. And what do you know? It says c is equal to -1. So in fact, k of x is this. All right. All right. So we need to evaluate each integral using substitution. Oh, they just straight up tell you. All right. Do you see a function inside a function? Yeah, you do. It's right there. It's natural log of x. Okay, that inside function is typically u. Okay, not always, but typically. So we're going to guess this. All right. Now we take a derivative. Du is 1 over x dx. And now we're going to start substituting. So the thing in orange, that's u. And that thing gets cubed. Now, the way I would like to do this is say, all right, 1 over x dx. Here's a 1 over x dx. So that stuff in yellow is right here. I'm going to swap it out for a du. du. And now, so this step was me substitutioning. This step is me doing calculus. Okay, I'm going to take the antiderivative. So I'm going to add 1 to the power, divide, plus c. Okay, and then I have to unsub. It's called back substitution. So u was ln of x. So we have ln of x to the 4th over 4 plus c. There it is, and we're good to go. Finally, here we are. Do we see a function inside a function? Yes, it's a little bit sneakier, but the exponential function has a sine of x sitting inside of it. We just, instead of writing it with letters, we just do this little e thing here. Okay, so that's going to be u. U is equal to sine x. So now du is cosine x times dx. And what do you know? Cosine x times dx, that shows up right there. So this is equal to, we have e to the u du. So this u is sine x, and this du is the dx times the cosine x. All right, but hey, this 0, this is an x value. And when x is 0, sine of 0 is 0. So this 0 is now a u value. And we got it by plugging in 0 to sine. Up here, we should plug in pi over 2. Sine of pi over 2 is 1. Okay, this integral is equal to this integral, which is sort of much easier. And the antiderivative of e to the u, that's still e to the u. And we should evaluate it from 1 to 0. You get e to the 1 minus e to the 0. And so you can just box that and call it good. Now, if this step confused you, there is another way to do this integral. And the write-up for that would look like this. So we have e to the sine x cosine x dx. So I'm just going to pretend I'm just now seeing the problem. And I would say, oh, you know what? I should first compute e to the sine x cosine x dx without limits. Okay, forget about those. Let's just find an antiderivative. And this is where you'd say, okay, well, u is sine x, and then du is cosine x dx. And you'd say, okay, well, this is e to the u du. And you say, oh, that's e to the u plus c. And then you back substitute and you go, oh, so this is e to the sine x plus c. And you go, aha, so I have an antiderivative. And then I'd hop back up over here and I'd say, okay, this is e to the sine of x between 0 and pi over 2. And then you'd plug that in. You'd say this is e to the sine of pi over 2 minus e to the sine of 0. And you'd box that and be done. And notice, so this is either the same thing, because sine of pi over 2 is 1, and sine of 0 is 0. But instead of having to do this back substitution step, you can just change the limits. You can just do this and just keep marching forward. Okay. All right, last page of the exam. Sweet, almost done. So a population changes according to this graph. So we have a p prime. Okay, hundreds per year. That might be important. Sketch the rectangles for a left Riemann sum with 3 rectangles, and we're between 0 and 3. Okay, here's 0, here's 1, here's 2, here's 3. So I'm going to put down some dividers. I'm not sketching rectangles yet. I'm just going to put down dividers. All right, now I'm going to be in my first set of dividers. And I go to the left wall, okay? So here's the left wall. And I go from the x-axis up to my curve. And that tells me the height of my rectangle. And then I go over. And so this is my first rectangle, okay? I drew way more than I had to draw, but that's just because I was trying to emphasize where to look, okay? So I like to imagine dividers. And so then I know to go to the left. So I'm on the left divider, go up to my graph, and that tells me how to make this rectangle. Okay, so now I'm between these 2 points. I go to the left, so I'm on this divider, and I need to be where this divider hits my graph, and what do you know? It's right here at 0. So this is sort of a trick question. The next rectangle is called a degenerate rectangle, and we're really just looking for that line. So in fact, I shouldn't have this here. And we're going to actually need you in a moment, but I shouldn't have this here, and I shouldn't have this here, but whatever. So we're now going to look between 2 and 3. And we go to the left side, which is 2. And we go to where we hit our graph, and we come over. And so now this is sort of our next rectangle. All right, there it is. I've drawn it. All right, compute, or given that p of 0 is 20, use the fundamental theorem of calculus to blah, blah, blah. All right, so this is a very sneaky question, but if you take the antiderivative of p prime of t, okay, then, so if you take it from 0 to 1, then what the fundamental theorem of calculus says is this is going to be p of 1 minus p of 0. Okay, so the fundamental theorem of calculus, if you have an antiderivative, and p is the antiderivative for p prime, right? I've undone the derivative. Then you plug in your upper limit, plug in your lower limit, take their difference. So here's the fundamental theorem of calculus. We want to use it, okay? So what do? We're trying to find p of 1. So let's solve for p of 1. P of 1 is equal to this integral here, integral 0, 1, p prime of t dt. Okay, this is a number that we have to figure out, plus p of 0, right? I move this over to the other side, and I get p of 1 alone. P of 0, by the way, is 20. That's a number that we know. Fine. So let's figure out this number. This is the area. The area from 0 to 1 underneath our curve, between the curve and the x-axis. That's a triangle. It has base 1, height 1. Its area is 1/2. So this whole crazy looking thing, it's the number 1/2. P of 1 is 20.5. Okay. All right, use the graph to compute this area. Include units in your answer. All right, let's do that. What is this? 1 to 4. 1 to 4. Okay, so here's this. All right, so we'd get all this area plus all this area. But, sorry, I should do maybe something like this and this. Just, it's not this stuff, okay? 1 to 4. Anyway, this has area positive a half. This has area negative 1. It's a triangle. The base is 2. The height is 1. You do 1/2 base times height. Sorry, the height is negative 1. You do 1/2 base times height. You get negative 1. Okay, and then we add this number and this number, and you get negative a half. Negative 1/2. Okay, we need to include units. So, p prime of t, that's the y-axis. The y-axis units are hundreds per year. The x-axis, it's implicit, but implicitly these are in years. The units of area are the units of y times the units of x, which kind of makes sense. That's how it works in real life. If you have centimeters here and you have feet over here, the area of this rug is a centimeter foot. X units times y units. Okay, so this is 100. And then, that works. Okay. Yeah, whatever. It's silly. All right, use the graph, compute the average from here to here. So that means we have to take the length of our interval. All right, look, we get the total area, 0 to 5 p prime of t, dt, and then we divide it by the length. That's the computation we need to do. All right, fine. So let's do it. So we're over here. Move away, move away. Boom. All right, we need all the area. We're going from 0 to 5. Notice this positive area plus this positive area would fill in this negative area. All that cancels. And in fact, if you add up the total area from 0 to 5, p prime of t, it's just this rectangle here, which has height 1, width 1, so the area is 1. So this monster is 1. So now the average value is 1 over 5. Okay, the over 5 is from this. So boom, there it is. All right, that's it. Good luck on the final, everyone.